welcome back to the Infodump, the series where I do a deep but not necessarily scholarly dive into a particular topic. Now, of course, we are continuing with our first topic of physics, and I remembered to do that bit this time, thank fucking God. I have decided to branch out, quote-unquote, a little bit from what you might consider traditional physics. This is going to be an episode on the physics of basic chemistry. We're not going to get into hydrophobic or hydrophilic compounds or anything like that, because even though all of that is very much grounded in physics, I do feel like it is more appropriate to have that be part of a series on chemistry rather than on physics. I will touch on it lightly here, but that is just your disclaimer so that you are forewarned. Now, what exactly are the physics of chemistry? Well, we've touched a bit on how electrons and protons have opposite and equal charges, despite having very different mass. Protons are also one of the two nucleons of atoms, one of the things that sit at the center and between, gravitational pull and attraction, keep the rest of everything sort of in line, as it were. Electrons are the thing that allow chemistry to work. See, when we talk about chemistry, the first thing you need to understand is what's called ionization states. In a neutral ionization state, or a non-ionized state, as it is more often called, an atom has just as many electrons as it does protons, meaning that it has a total net charge of 0. The fact that this equilibrium exists helps explain why it's generally thought of as sort of the default, right? Because, again, going back to our mental image of magnets, because electricity and magnetism are very tightly linked through electromagnetism, if you have a magnet with the south side and a magnet with the north side facing each other, they will pull together. So, when you have negatively charged electrons and an atom that has more protons than electrons and therefore a net positive charge, those stray electrons will be attracted to that positively charged atom, thus filling it up until you have a neutral charge. Likewise, if the atom has too many electrons and is negatively charged, those electrons will start being repelled by the electromagnetic forces of the other electrons more than they are being drawn in by the attractive electromagnetic force of the protons. So, essentially, what this means is that these more further away from the norm, I guess, further away from neutral charge, atoms, or rather ions, because an atom is specifically only a neutral ion. These neutral ions, these atoms, don't attract anything, but the further away you get from that, the stronger that attractive or repulsive force is going to be. Additionally, when we talk about chemistry, we have to understand something else, which is that the state of atomic neutral charge is actually secondary. Even though it is over time what atoms will trend towards and what ions will trend towards, it is in the formation of chemical bonds not at all important. Not really. What is more important is an atom's electron orbitals, or to use the quantum term, its electron energy levels. If you remember what I talked about when I said that electrons work more as a cloud of probabilities that take on certain shapes, this is where that really becomes important. Because, unsurprisingly, since electrons repel each other, you can only have so many electrons within a certain region of probability before you just can't have any more in there. Now, this is also where quantum mechanics starts becoming important, specifically in terms of the photoelectric effect, which is the effect that transfers energy between electrons and photons. Because, see, the further away those electrons are from the most central portions of the atom's nucleus, essentially the quote-unquote further out the orbitals are, although once you get into larger atoms, they start looking really weird and not at all like rings or spheres. Instead, they look like, well, what you'd expect from four-dimensional spatiotemporal shenanigans to create in terms of an interference and probability graph. But yes, the smaller scale is much more like, spheres, and therefore much easier to visualize, at least when you don't have a good understanding of how it all ends up looking. Regardless, the further away from the simplest orbitals, the more complex you get, and the further away from the nucleus you get, the more energy, essentially, is in each electron. Regardless of where it is within its quote-unquote orbital, within its little cloud, it has more energy than an electron in a cloud that is simpler or closer to the nucleus. In other words, when you put energy into electrons, they will actually move to higher energy orbitals. And when they move from a high energy orbital to a low energy orbital, for whatever reason, they emit energy. That energy will almost always come and go in the form of light. There are a couple exceptions, but they only really occur in fairly extreme situations, so we're not really going to get into them. Point being, though, that electrons, when they interact with photons in this manner, either absorb energy and just turn it into heat for the atom, or they emit energy, sometimes turning the heat of the atom into light. That's how things can be glowing hot. That's, well, how we get lighting, right? Or most lighting anyway. Heating up a material to be so hot that it's literally glowing. Essentially, what's happening here is that when a photon hits an atom, depending on the ionization state and all the stuff around it and the exact material type, like solid, plasma, gas, liquid, semi-solid, non-Newtonian fluid, etc., depending on the energy of the photon as well, it will deliver a certain amount of energy to that molecule, to that atom, to the electrons specifically, because they are on the outside and therefore they're the things that are most likely to get hit. Now, when this happens, the electron can either be forced up an orbital, essentially, or more, gross oversimplification here, but essentially, the electron can either be forced upwards in energy level, or, and this is where the quanta, the discrete energy units, are important, if the energy delivered is not enough to force it to reach a higher energy level, it will simply be just lost in the form of heat. So why is this important? Well, first off, it helps establish that heat and light via atoms and electrons are somewhat interchangeable. Somewhat, not entirely. There is still entropy to consider. There is still the laws of thermodynamics to consider. But you can heat something up to the point where it is glowing, and you can shine a light on something to make it hot. As I am sure anyone who lives in a place where you have an actual fucking summer can understand after going outside barefoot. That is why we have heat on this desolate rock of a planet. It's because of the light, not because the sun is somehow radiating heat this far out. Sure, so a good chunk of the light from the sun isn't in the visible spectrum, but most of it is higher energy, not lower energy. Very little of it is actually in infrared, which is the spectrum of light that just goes straight to heat because it interacts with the nuclei of the atoms rather than with the electrons. Sort of. It's, again, more complicated. But essentially, that's the first key thing, is that light and heat are semi-interchangeable. The second key thing that we learn from this phenomenon is that electrons are basically locked due to, well, all of the various forces that surround them into those discrete energy levels. They cannot exist in some sort of flux space in between. And any energy delivered by a photon that is not that is essentially in excess of the amount needed to be at a particular energy level is lost. So if it's, just one infinitesimal energy unit shy of moving up to the next energy level, all of that energy is just turned into heat. However, this is also how we are able to see things, how we are able to, visually interact with the world. We can look around, and what we see is often referred to or contextualized as light reflecting off of objects. But that's not exactly accurate. It is mostly accurate in terms of that's generally how we think of reflection, and so it sort of defines itself, paradoxically. But a more intimate look at it is essentially that most materials, when you point light at them, will absorb that light into their electrons and then emit a good chunk of it back. Now, the color that it's emitted back in varies depending on the material, depending on the consistency, depending on the level of light, and all of that. But because different colors of light are determined by wavelength, i.e., the amount of energy in each photon, what that tells us, essentially, is that each individual photon we see, or that we interact with, if it's bouncing off of something, has been emitted by that object. That is how color works, essentially. When we, take an object and look at what color it is, we are seeing usually mostly white or broad spectrum light being shot at it, which then is mostly reflected, but only in particular spectrums, only with particular colors, particular groups of wavelengths. And some of that incoming light, yes, is turned into heat. But most of it, even what is outside of the spectrum that the object, quote-unquote, reflects light in, is being absorbed and then re-emitted in that spectrum. That is why you can shine a light of a complementary color on an object and still actually see light coming off of it. Now, to be fair, nothing, not even quote-unquote matte black objects, actually have a perfect light absorption rate outside of what they reflect. The closest you can get to that is with those matte black objects that just absorb all light, except for a tiny little portion. The closest thing to a pure black that we as humans have been able to artificially create is several orders of magnitude from reflecting all incoming light, but it's not, and never can be, complete absorption. The only way you can completely absorb all incoming light, as far as we know with modern physics, is by having a black fucking hole. Because those eat everything. The light's not getting turned into heat, it's just getting ate. So yeah. There you go. Little bit on the optics, or rather the physics of optics. Not the optics of physics. The optics of physics are... That falls under the communication and PR category, not the hard science category. And I say this as someone who has majored in both communication and physics. It's not a real science. It's more of an art than anything. It should be treated like one. Sure you can... Anyway, that's a rant for another time. What is important here and now is getting back on track and explaining how all of this optics stuff actually matters to chemistry. And the answer is pretty simple and straightforward. These discrete energy levels want to be internally stable. I say want in sort of an anthropomorphizing with... I can't talk. Anthropomorphizing way. I think that's right. Anyway, the discrete energy levels are most stable when they have particular numbers of electrons in them to create a sort of even distribution and even balance of the electric repulsion, or electromagnetic repulsion rather. Think of it sort of like how, yes, you can theoretically sit on a stool with one leg, but for the most part, the more legs that stool has, the better, until they start crowding each other out, at which point you end up not being able to sit on it at all because, well, it'll collapse under its own weight. So, the stool analogy isn't the best. I think it works better for helping to understand why not having enough is a problem more than it helps for understanding why having too many is a problem. But, I mean, just thinking with magnets makes it a lot easier to understand why having too many is a problem, right? You try to have a box full of magnets that are all, all have a external side that is south and an internal side that is north, or other way around, and that is literally just a magnet bomb waiting to happen. Run and take cover. But yes, I guess another way of putting it would be like there's only so many legs you can put on the stool before it doesn't have room for any more legs, right? Because you physically can't have more than a certain number of electrons in a given energy level. They just don't fit. They crowd each other out. So, yeah, having that, having that sort of stool analogy, whether it works for you or not, in mind, should help you understand exactly how a lot of these systems and mechanics work. Because Next, we have to talk about why chemistry works the way it does, why these particular atoms behave the way they do, why ions behave the way they do. So, when you have an atom with a neutral ionization state that includes unstable electron orbitals, well, that's kind of a recipe for conflict, right? Because the electron orbitals are trying to draw in more electrons in order to be stable. There is sort of free real estate, as it were. However, at the same time, those electrons are also pushing each other out because of the electromagnetic repulsion. Like I said, generally speaking, the stability of the electron clouds or electron orbitals for chemistry is more important. In general physics, that is very much the opposite. But when we are dealing with chemistry, we are dealing with the interactions between two different atoms, or two or more different atoms, with different stable ionization states, essentially. So if we take the most infamously reactive elements, the, alkaline metals, and the more reactive among the halogens, the various gases that, well, most of them are gases anyway, that we often pair with them. For instance, everyday table salt, sodium chloride. Sodium is an alkaline metal, and chlorine is a halogen. And they fit pretty much perfectly together, because sodium has an electron orbital with basically nothing in it on the at the highest level, or the outermost shell, whichever one you want to think of, whichever way is more intuitive for you. So if those electrons can find somewhere more stable, they will move towards it. Chlorine has an outermost shell, a highest energy level, that is just shy of hitting its peak stability. So, if there's an electron that wants to come along and help out, well, that's much appreciated. But of course, when we get these atoms trading electrons between each other in order to meet their stable ionization states, that gives the atoms themselves charges, which means that now the atoms are attracted to each other via electromagnetic effects. So, keeping with our, example of table salt, right? We have one positively charged sodium ion and one negatively charged chlorine ion. Well, it just so happens they have equal charge, but opposite charge. So, as is the case with electrons and protons, that equal and opposite charge causes them to be drawn together to form a single molecule with no net charge. Internally, of course, they do still have differing charges, but the molecule of table salt does not. Where this all gets really fucky is water, because water, on top of being abundant and liquid at most temperatures that aren't, extreme by the standards of life, which requires liquid water to live, so, kind of walked into that one. But anyway, water is liquid at much, much, much broader temperatures than anything else of its composition type. And that is because of its very unique structure, which also gives it a bunch of unique properties. Water is called a polar molecule. If you've ever been in a chemistry class or looked at chemistry slides, you will recognize it as the funny Mickey Mouse ears molecule. Or at least that's what everyone in my chemistry classes back in high school recognized it as, which I always thought was stupid, but okay, I guess I'm doing the bit now. Anyway, water is unique because it is made up of one oxygen atom, or rather one oxygen ion, and two hydrogen ions. Now, it's more unique because oxygen forms what's called covalent bonds, which is where essentially the electrons are in both atoms' clouds at once. It's not exactly sharing or double dipping or any other euphemism you can come up with. It's closer to a form of superposition, but not quite. Essentially, it means that there is an overlap between the electrons of one atom and the electron orbitals of the other atom. So there isn't any actual ionization happening, at least not for the oxygen, but there is sort of pseudo-ionization happening. Covalent bonds are very, very difficult to break. The strongest bonds known to man in natural chemistry are triple covalent bonds. This is what nitrogen gas has. That is why the development of things that could break that bond and create fertilizer, and also deadly chemical weapons, was such a huge deal. So, yeah, covalent bonds, because they aren't based on the individual charges of the atoms, or rather the ions, but rather on this sort of enmeshment of their electron clouds. Well, that enmeshment makes them much harder to break, but it also gives those molecules created by covalent bonds some weird structures and properties some of the time, and water is no exception. The water molecule actually ends up being polar, because with the draw of the electrons into the oxygen rather than the hydrogen, this means that the single electron each hydrogen atom has is essentially held on the side of the hydrogen atom facing the oxygen atom. Additionally, in order to reach that stability, essentially what happens is that these hydrogen atoms end up being pulled closer together, creating a sort of pseudo-charge, in a sense, on one side that is positive, and a pseudo-charge on the other side that, in order to maintain the internal neutral charge, is negative. So, essentially, what ends up happening is that water, due to its very weak but still definitely there polar structure, is able to, by being a liquid with a polar molecular structure, break apart almost any ionic bond. Very tough ones are, of course, going to be stronger than the weak electromagnetic polarity of a single water molecule can handle. But that is why water is such a reliable solvent. It just rips things apart. Even if they've got covalent bonds, they're not necessarily immune. They'll just very gradually be eroded by friction if they're in running water, or have everything around them be ripped apart by those polarity, by that polarity, and gradually, well, get dissolved. This is also responsible for the formation of very weak hydrogen bonds, as they're called, which is part of what leads to stuff like stiffness in clothes. Hydrogen bonds are not really even proper bonds between atoms. They're better described as bonds between molecules. And that is really where the physics of chemistry starts going into more applied chemistry that's not really that interesting. But essentially, the polar structure and the polar nature of water is responsible for basically everything that is able to work. Like every bit of life, everything more complex than individual lone simple molecules is to some extent due to water and its polar structure. Water dissolves everything, and from that solution, new things arise. Which I think is a pretty good note to end this week's episode on. So, with all that said and done, thank you very much for watching and or listening, and I will see you all next time.